Julian, who is with us, works as an application development engineer at NatureWorks, where he's all about creating new products and helping customers across Europe with technical know-how. With over 15 years of experience in the world of biopolymers, both hands-on and on the business side, he knows his way around sustainable materials like few others. He was previously with Mitsubishi. In the following, Julian Schmeling gives us an exciting insight into the world of flexible packaging and, in particular, the use of biopolymers in this area. Please join me in welcoming Julian Schmeling from NatureWorks with his presentation on the topic Ingeo grades for plastics processing, the latest trends. Welcome, Julian.
Thank you. Yeah, thank you very much for the kind introduction, and it's really great to be back. Thank you for giving NatureWorks the opportunity to speak here. And yeah, the title is about our latest trends that we have developed application-wise, but the focus here will really be on our latest developments in biaxially oriented PLA films. So I guess, and I hope most of you know NatureWorks. I mean, this morning session, I've been happy to hear that we are considered as one of the pioneers, because basically what we do for more than 20 years on a commercial scale is to produce a 100% bio-based and fully biodegradable material, which is PLA, and that we produce under the brand Ingeo. And there are a couple of grades, a range of grades available for the most relevant processing technologies. To give you a scale about what we are producing and what scale, so for more than 20 years we have been producing our PLA in Blair, Nebraska, with an annual nameplate capacity of 150,000 tons, using corn as a feedstock, which is basically the plant is located right in the middle of the cornfields, so that's directly where the feedstock is grown. And then talking about our current investment, we have been starting to construct a new production plant in Thailand with an annual nameplate capacity of 75 kilotons. That will be an integrated plant, also doing our own fermentation of lactic acid. And here we will use sugarcane as a feedstock, because that is the crop mostly grown in the northern part of Thailand. And that will put NatureWorks really in a unique position, because we will be the only PLA producer globally being able to supply the same range of grades from different regions. And that means that we are also well prepared to overcome certain issues in the future, thinking about supply chain limitations, for example. So I guess you're also familiar with the most common applications where PLA is being used today. Traditionally, it has been used in food serviceware applications, so it can be transformed into clear, transparent, rigid food containers, cold cups, for example, as well. But in the recent years, we have also looked at more, let's say, technically challenging applications. One of those is certainly the coffee pot, where you require a certain amount of heat resistance, and that has been achieved by a new development of grades that can achieve that. But also the fiber and nonwoven space, we have developed specific fiber grades for that to achieve heat-resistant fiber grades that can be used in tea bag applications. And that is, by the way, in the common current PPWR, one of the mandatory compostable applications. PLA, due to its performance, is also being widely used in 3D printing. It has become actually one of the incumbent materials for that sector. We have a range of grades, we have a portfolio for different technologies as well, and recently we have also launched a new grade called 3D 300, which is a high-speed printing grade. This is really one of the latest trends in the industry to increase the printing speed, and we have launched a grade according to the needs of the industry. And then here also talking about extrusion coating, paper-related applications are especially important because yeah, let's say in the flexible packaging world, there's a lot of paperization ongoing, so transforming packaging that has been traditionally made of plastic into a paper-based solution. But obviously, those paper-based packaging always need a coating, a barrier, a functional coating on top. And we have recently launched a new grade called Ingeo 1102, which has been specifically designed for the extrusion coating process. PLA, as such, has been very challenging to process in this process technology, and this grade overcomes the challenges. And it's industrial compostable. We have also repulpability certifications currently in the US. And we are also working on improving that grade further, for example, enhancing the biodegradability and also the repulpability in Europe. So, but today the focus should really be on flexible packaging, as mentioned, and also the impact of the packaging and packaging waste regulation may have on especially the biaxially oriented PLA films. So the world of packaging is a big world of various processes. Flexible packaging can be produced in cast film extrusion oriented MDO films, blown films, and biaxially oriented films. And with that niche of biaxial oriented films, we have developed and placed on the market compostable biaxially oriented films with our partners. That is in the market actually for many years. So a biaxially oriented film is a film that is post-stretched in both directions, in machine direction and in transversal direction after extruding the film, leading to lower thickness and special mechanical properties. For many years, this kind of film has been used in food packaging applications, especially for fresh food and vegetables, but also bread bags combined often with paper or label applications. But what we see in the PPWR, and while it's limiting a lot of applications and only defining certain applications to be mandatory compostable, we see also a lot of opportunities here in the areas of small format packaging and condiments, as well as lidding films for coffee capsule. Why is that? So flexible portion packaging and small format packaging in the HoReCa sector, dine-in, will be banned if it's made out of plastic. So the only option could be to make it in a paper-based structure, or if the member states allows it, it could also be accepted to be compostable. And those applications require certain barrier properties, as you can imagine. Also, the small format packaging, the lidding films here could be made of a BOPLA film. The example that you see here, that is already on the market commercial. It's a spreadable chocolate, which is being commercial in Italy already for a while. And then also talking about coffee capsules, the PPWR mentions the paper-based coffee capsules where you also need a lidding film, and there BOPLA could be part of the structure. But I would also like to highlight that we are not only talking about Europe here, because those developments are also spreading to other regions as well. We see a strong growing demand in the US, and we also see a strong growing demand in Asian countries, for example, in India. So today, BOPLA films offer quite interesting properties. The material is fully bio-based, industrial compostable. It's very stiff, and also due to the processing, can be extruded in a heat-resistant version, but it comes also with certain limitations. And one of the limitations, especially connecting with the previous applications, is the barrier performance, talking about moisture and oxygen barrier. Another point is the biodegradability of the material. As we heard in the previous presentations, PLA is industrial compostable, but there's also an ask to improve that to a quicker biodegradation. And then last but not least, very important, obviously, is also the productivity, because it's directly related to the cost. And therefore, we have developed a new grade, which we call Ingeo Extend 4950D. That is a grade that has been specifically designed to be used in the extrusion process for BOPP, which is especially challenging because it requires high stretch ratios. And I will go into more details in the next slides. But first of all, what is really important for us, and that is not only relevant for this specific development, has been to work in collaborations with industry partners. And I think that is also known to many of you, that we need to work in collaborations along the value chain to be successful in certain developments. And in this specific case, we have been closely collaborating with Brückner Maschinenbau, which is the leading manufacturer of stretch film lines globally. And we have been strongly collaborating with Sukarno Master Batch, based in Switzerland, which is a specialist on functional master batches, and especially also talking about functional biopolymer master batches. So with that collaboration, we have been achieving many milestones already, close to industrialization, and we are also planning to show some very nice and interesting examples during the K show this year in Düsseldorf in October. And yeah, going no more into the technical details, what you see here on the left-hand side is a typical BOPLA structure, 20 micron thickness. You have the core layer and you have outside the sealant layers. And the new development contains in the core layer 20% of our new Ingeo Extend grade. And then in the sealant layers, you have specially designed master batches from Sukarno. Those are designed to not affect the transparency of the film, but to adjust the anti-blocking properties, to adjust the COF, so the coefficient of friction, and at the same time to not, let's say, decrease the performance in terms of metallization and lamination behavior and adhesion of such technologies. Talking about productivity. Today, a standard BOPLA film is stretched at a maximum of 4.5x typically in transversal direction. And what you see is that by adjusting the formulation with this new grade, we have been able to increase the TD stretch ratio to 7x. So that's a major improvement. It's really significant. And we are trying to further improve that in order to reach really the target level of BOPP films, which is stretched up to 9x. And what that means for the productivity of the film, you can see on the next slide. This is just a simple example, considering you have a film 20 micron thickness, running at a line speed of 246 meters per minute. And then comparing a 4.5x stretched film versus a 7x stretched film. And you see that the output is increased by 56% due to the higher stretch ratio, which results in a higher width film and therefore increasing the productivity. Also very important for such films is the heat stability, and we just heard that PLA has limitations in that. What you see on the slide is various formulations that we have developed. The left-hand side is a sequentially stretched material, and on the right-hand side in red is the simultaneously stretched material. And due to the processing technology that we have applied, for example, by annealing the film in the extrusion or after the extrusion process, we have achieved heat shrinkage at 130 degrees C for 5 minutes, which is well below 5%. And that has been really a great achievement if you consider PLA as a not heat-resistant material due to the annealing process and also this strain-induced crystallization that you can generate in the process. We have really generated a film that is very heat stable. But this is not the only important part here to talk about. Also, other properties are really essential for the post-processing especially. And that's on the one hand side is the coefficient of friction. Here, the target was to be below 0.8, but this can still be adjusted by choosing the right master batch and the concentration, and then also the haze, which directly translates into the transparency of the film. Target is here to be below 4% haze, and you see this all 4 formulations that we have developed. We are below that threshold. So means that those films are really highly transparent. Also, the surface energy is important. You should be above 40 dynes per centimeter in order to have a well-printable material, but also if you look at subsequent coating technologies or lamination, you need a certain surface energy in order to have a good performance and adhesion of those coatings. Then talking about the biodegradation, so what we found is that this new grade, Ingeo X10 4950, shows 8 times higher hydrolysis speed compared to a standard PLA grade. And the hydrolysis speed is directly linked also to the speed of biodegradation. That has been tested at 50 degrees C, so it means it's not under home composting conditions. This is really important here to mention. But it should certainly help to overcome the challenges that some may have with PLA and the slower degradation. Obviously, if you are, for example, at the borderline with certain structures and need some faster degradation, that could really help to speed up the process. And yeah, for the applications that initially have been mentioned, barrier properties are a must. They are essential. And unfortunately, most of the biopolymers have a quite high moisture transmission rate. You see it here on the x-axis. This is a commonly used BOPLA film that's quite outside the requirements that you have for such applications. And by applying certain coatings, you see that the simultaneously stretched film has even better performance. So the water vapor transmission rate has been between medium and high barrier, so an excellent result already. Also important to highlight here is that we didn't use any primer. So we have directly metallized the films without using any primer, which is also important for the cost of the product. But also many primers are not compostable certified, so it makes it quite easy for us to be more efficient in that respect. Also, the oxygen barrier is in a reasonable level, but you also have to mention here that the focus so far has been on the reduction of the moisture barrier. And in the next step, we will work on also improving the oxygen barrier. Target will be really to achieve barrier levels of, let's say, in the high barrier or even ultimately in the ultra-high barrier areas. So summarizing this, the product runs on BOPP lines with high outputs. We have achieved film thicknesses of well below 8 micron on the recent trial. On the pilot line, we have extruded the material below 5 micron even. And that makes it also interesting for certain lamination processes. For example, if you would combine it with paper and you want to have a very low amount of polymer in the structure, that makes it quite interesting, I believe. Yeah, we have significantly improved the barrier properties, faster biodegradation achieved, and by using the right master batches specifically designed for the process, it can be easily also processed in secondary processing steps. But just as a last comment here, this material is not limited only to BOPLA production. If you think of any other applications where it could be a benefit, I'm very happy to discuss about it. We are also testing it in other applications, and I would really be happy to discuss about your ideas and suggestions. And with that, I would like to thank you very much for your attention and looking forward to your questions. Thank you.
Yeah, thank you very much, Julian Schmeling. This is the biodegradable power pot,
PLA
flower
based?
flower pot for you. No, maybe you can ask Peter Putsch about this.
Doesn't feel like PLA, yeah?
No,
Thank you.
but thank you.